And today we enter the next topics that we entered vector calculus after the triple integrals and change of variables, and we worked on this line integral, right? And the second thing is the surface integrals. It's main motivation for line integral work calculation. For surface integral, it's called the flux calculation, and I spent some time today to explain this flux, a notion of flux in physics in detail, right? So do you know what this technical thing that we'll be focusing on after I introduce the meaning? At least you know the meaning of this thing. So that's sentence that they start Stokes' theorem, and they state it like this. And let's go over the sentence. Here's a line integral of a vector field. No problem. We know what this means, right? Okay, around the boundary of a surface, not region, but surface means piece of, elliptic paraboloid. Remember those things, elliptic paraboloid? What was the equation of elliptic paraboloid? Z equals x squared plus y squared is a typical thing. You can throw in some constant here and there, shift it up and down, but all elliptic paraboloid, right? So if it is a piece like that, and that's what they mean by surface in space. Not like parallelogram, flat one is a curved surfaces sitting inside three-dimensional space. This one is sitting inside the three-dimensional space. That three-dimensional space is called ambient space. But if you live inside the surface, not being able to see outside the world, the surface object itself, removed from the ambient space R3, is called two-dimensional. Does that make sense? The surface itself is a two-dimensional, but it is inside the three-dimensional space. Okay? So that's a surface. Line integral around the boundary of a surface. This is familiar, right? Where do you see this one? Line integral around the boundary. What theorem? Green's theorem says, line integral around the boundary of that region in that xy plane, but that region is no more in the xy plane. Where is it? Yeah, you throw this handkerchief in the air. That's the surface. The boundary is the edges of that handkerchief right at some moment in the air. That's the surface. Is equal to what kind of integral? Not double integral, right? Double integral, that would be just Green's theorem, right? But it is something called surface integral of whatever some vector field they're talking about. So you can see this is Green's theorem lifted to ambient space, three-dimensional ambient space, right? But the nature of calculation is the same as Green's theorem, but it is just happening not in xy plane, but in xyz space. What is this theorem called? Stokes' theorem, right? So let's understand the detail of this one. I want you to look at this one as here's water passing through this one here. So it has some thickness. Maybe deep down there, it flows slowly because of the bank in here. The water on that side, because of the friction, the speed is slower. Inside, it flows a little bit faster. To that side, goes a little bit slow. So I guess this vector is indicating the velocity of the water molecule in there. So this picture makes sense? Okay? That's easy to understand, but we're going to turn the meaning of this vector, which is equivalent to the velocity, something different. I'm going to take a little plate or net, like fish net. It is exactly one, let's say the certain size, 1 inch squared. And I place it right here. So this is the direction of the flow perpendicular to the direction of this flow. So from the top, you only see this thing, right? But if you go to the other perspective, you see water is directly hitting perpendicular to that plane, right? And then I use 1 second to measure the number of water molecule passing through this one directly as you place it in there. Turns out, turns out there was a 2 million particle pass through. So I'm just going to use 2. Okay? So this vector is actually going, this is the direction. The magnitude of this one is indicating the magnitude of that vector there we change the meaning of this velocity vector to the number of particle that is passing through. Let me use that word. Just do the experiment. Number of particle that is passing through that region over there over 1 second. The number of particle we measured is 2 million and divided by this area, which is 1 inch squared, right? And then I take that position and make it a little bit smaller, okay? And then measure the second value of the number of particles passing through the smaller region and divide by the area, right? Take an even smaller region and divide by even smaller area. And if you keep doing that, what's going to happen to the number of particles? It's going to be again smaller and smaller, right? What about the area down there? It's becoming smaller and smaller. It's a quantity approaching 0 divided by a quantity approaching 0. What is the official name of that kind of phenomenon? Indeterminate form. So what is the conclusion about indeterminate form? Inconclusive. This is not enough information to conclude about what's happening. But if that exists, that's the density, the idea of density in there, right? So I'm going to call that one fluid density, scalar fluid density. So this vector indicates direction of the water particle at that moment, and the magnitude of the vector is indicating, what do you think it's indicating? The density itself, right? So this is a velocity vector. Now we change the name of this vector to fluid density vector. Fluid density vector. So if you put tiny amount of it in the perpendicular to the direction, and the fluid density is this one. So if I have tiny one, area A, if I want to measure number of particles that's passing through perpendicular per 1 second, how do you calculate the number of particles in there? Is the density, which is indicated the length of this vector, times, what do you multiply? To get the number, density times the area, right? The area is what you multiply. So if you are seeing this one as a 2, that means there's 2 million particles passing through per square inch perpendicular. So if you want to measure over smaller area, then you have to multiply smaller area to that scalar density, which is absolute value of that. So this is a velocity vector. Now we called, what was the new name? Fluid density vector. The key thing is that you have to understand this perpendicular direction. So idea makes sense? So I summarize it here. So let's write this one down, all of you, and sink this one in, and think about one more time if everything here makes sense. Here's a picture. Sometimes it flows through fast. Different meaning. Fluid density vector. So V is a density vector of the fluid per second. The second thing never changes. We fix that part. The direction of this vector V means the direction of a flow. The absolute value, the magnitude of the vector now is interpreted as the number of particles. If we just write 2, we're going to think of it as 2 million. Passing through square region, this is sensitive part, right? It has to be perpendicular to that direction and per second. That's the meaning of this vector. Then with this information, how can we actually calculate number of particles that is passing through area that's very small, like with the area delta A? Then simply multiply that scalar density to that area, then that tells you the number of particles passing through. It takes too much time sometimes to rewind all these things every time when you do the problem. That's not a very good idea. So try to understand the meaning at one point and memorize this appropriate formula and think efficiently and handle problems efficiently. It's always about this, balancing out these two things makes learning mathematics more fun, right? So this makes sense? So there are two ideas of a density. The vector density, right? Vector density includes directions as well. And there is a scalar density. This is actual number in there, right? But there's a sensitive part about it has to be the right direction in there. Any question? about this idea? So new vectors were introduced. I started with a direction vector, a position vector, and placement, displacement vector, and velocity vector, acceleration vector. What was that after? Force vector, right? And then now here is a density vector is introduced. All right, here it is. So this picture here is indicating density vector. Let's say that length is 1. That's exactly 1 times k vector. Makes sense, right? K is this direction. There. This is exactly 1 inch. And here's 1 inch. Okay? So after 1 second, how many particles is passing through this entire plate? If the vector is this. That's the density vector. This is 1 inch by 1 inch. After 1 second, how many fluid is passing through? 1, right? Let's say 1 million particles passing through. That makes sense? So if I choose this guy right there and ask you to measure how many particles pass through that guy over there, that's that side. So what was the formula again? Let's think about a formula. This is scale. That's how many things pass through, right? And multiply by delta A, right? So what is the size of this length of the vector? 1. What is the area of this one? 1, 2, 3, 4, 5. 1/25th, right? And 1/25th. That's it. 1/25th million particles passes through that, right? Often it's easy to see that because all is constant, but later if there's changes, I'm going to do that calculation, and I'm going to do that calculation over here. I'm going to do that calculation over there. What is the idea of this one? And dicing like this and putting them all together, the famous the Riemann sum. All right, Riemann sum's back. Of course, you knew it. Integral is all understood like this. So, summarize it here. The V is equivalent to actually the velocity of a fluid, right? Because if you place your plate there, if it's moving fast, of course, more particles passing through, right? And if you place the plate over there directly, if you're moving slow, of course, per 1 second, fewer number of particles passing through. That's exactly equivalent idea, but it's a different name here now. And this is a constant, right? But you can imagine if I choose that point in somewhere in place, x, y, z space, the fluid is flowing this way. If I choose this point, they're flowing this way. So all different. And then the vector field of what? The density, fluid density vector, changing everywhere, right? That's more interesting thing, and that's the Riemann sum is absolutely required to handle that. So phi is now fluid density vector. So here's a picture from the book that following one particle, the history of one particle at a time. Here, if you just follow this particle in the water stream that move like this, right? And each time looking at the motion, you can compute the velocity vector. If it is fast here, you can imagine if I put the plate over there, you expect that the fluid density vector is higher, right? Make sense? So let me challenge you with this tricky one in here. If I put the plate over there like that, what do you think this scalar density vector about there? How many particles is passing through that plate? 0, right? It's just passing by and never actually cross that one. That makes sense? Yeah. So that's how things are changing to the direction of a plate. So what is changed? The density. All right. So I think I explained this. So let me use this picture to somewhere in between, not parallel, not perpendicular, somewhere in between in here. All right. So same thing is the density, fluid density vector is k, and this plate is not perpendicular to that, but it's slanted like this. We're actually looking at this one, and I'm looking at this angle being exactly 60, and this is 1 inch and 1 inch. Make sense? So who can calculate the length of this one in here? 60 degree, 90 degree, 30 degree, 1 and square root of 3, right? And here's a 2, so that's exactly length 2 of the side. So one question, if 100 1 million particles passing through over 1 by 1 here. Okay, so if I look at this entire region whose area is 2, right? How many particles passing through that? Still 1 million. If you think about it, right? So number of particles passing through in here is still 1 million. But the area over that is what? 2 times it, right? So area is 1/2. That means if I take a tiny piece of area there with area delta A, how many particles passing through that? 1/2 times the area, right? So what happened to the density? Density is shrunk by 2. But how about the number of particles passing through this entire thing anyway? That's the same, right? Okay, so we want to calculate the density. So if particles are passing through like that, this is the fluid density vector. What happened to what changed the density to that plate over there is coming from this normal vector. That's the direction, right? So let me give you a little picture. If this is a density vector, fluid density vector, your plane's normal vector is like this. What happened to the density? Number of particles. Scalar particle. That's the same as this one, right? Number of particles passing through that, right? That's the density. How about if this is the direction, if I turn it around, your normal vector is perpendicular like this. And what was the number of particles passing through that in here, which is same as density here? If I use it, yeah, it's a 0 there. And if you have this fluid density vector and somewhere in between n, if you measure carefully the 60 degree and what could be that angle here, it turns out exactly 60 degree, right? You can just follow through easy calculation for 60 degree. Then it was exactly half of it, right? Number of particle. That's number of particles. So about that. Number of particles 0 passing through. Number of particle passing through here is 1/2, right? A million. So we want to come up with a quick calculation. What should we do about these two vectors to measure these things correctly? Yeah, you just simply guess, oh, it seems like a dot product, and I'm going to skip that analysis. It's elementary analysis, but it's fun for you to do on your own, but let me skip that. So the answer is the dot product. The density is a dot product. So in general, if you have this density, a fluid density vector, if this is your normal vector to the plane there, and this is the angle theta, and what is, if I measure the tiny amount in here, what is the density, scalar density through that? How many particles passing through that part? The answer is this orthogonal projection of this V onto N. Okay? So let's remember orthogonal projection, not as a vector, but number of particles there. So remember it's orthogonal projection. We dot these two things, right? And then we have to divide it by length of that power. By what power? 1 or 2? If it is 1, if it is a scalar, if it is a 2, then you look at it as a vector, right? But we want just number, how much of it going through, and it turns out, if you experiment like this, and geometrically, it's easy to understand. That's new scalar density. That means if you sample, let me just like that. If you sample tiny region there with area delta A, how many particles are passing through that is exactly the number of particles passing through that tiny area with area delta A is this scalar times delta A. That's the number of particles passing through. Okay? Hope that makes sense. So I think that's what's written under there before. That's the direct perpendicular one. I probably wrote it somewhere. Oh, it's written here. So let me save this one quick, and I'm going to paste it here, what I just showed you. No, not normal. Normal vector is just a, yeah. There was a word to normalize. that means shrinking down to 1. The normal vector is not that normal vector, normalized vector. Any vector is a direction is a good point. That also confused me sometimes. So normal vector is not normalized, it's just perpendicular. So they called unit normal vector if you want and shrink to 1. So n here is not necessarily unit normal vector. So computing the number of fluid particle in xyz space, that's the, let's say that was the fluid density vector at that position in here. And it turns out parallelogram is ideal. So I'm going to look at it as a parallelogram hovering in the space. This side is generated by vector p. This side is generated by vector q. Suppose the density vector is all constant because this is going to be really, really tiny for the Riemann sum. But the density vector is not necessarily perpendicular to this guy. So I'm going to write it like this. That's where, different direction. And here's our normal vector n, right? So how many particles are passing through that is the following. First, scalar density of that is Vn dot with this n in here, right? That's if I sample even tinier the region over there, and this one multiply that region is the scalar, if it is scalar density of number of particles, if they're passing through with a constant for this small region, if you assume it's a constant. So this scalar density thing makes sense? Any question? Okay. Then to get the actual number of particles, you have to multiply the area, right? I want you to go back to the, session 1. And who remembers how to calculate the area of this parallelogram? That's right. But cross product is a vector, right? So what is the area of this one? This is a density, so you have to multiply this scalar density by the area of this plate, which is related to cross product, right? But what was the correct notation? Cross product, the length of the cross product of these two things happen to be the area of the parallelogram. Triple product. Remember that part. Alright? So that's the number of particle that pass through over how many seconds? 1 second. That's the formula. Alright, so I wrote it down. But, like I said, this normal vector choice, it doesn't matter how long you want one that you choose, the orthogonal projection is always the same, right? This one is projected onto that direction. That's always turned out to be the same. So it doesn't matter which one to choose. But what is if we have this vector p and vector q? What is the natural normal vector we should choose? This cross product itself, right? So we can even choose that n here in that context, the cross product itself, right? The normal vector is a cross product. The area of this one is the length of a cross product, right? So what happened to this formula? Number of particles is now, according to that, V is the fluid density vector, and we choose normal vector to be cross product there, right? Correct? And divided by the length of a cross product, multiplied by the area of this plate, right? What is the area? It's the length of the cross product, and they cancel, giving you amazingly elegant formula. If you have this side p vector and that side q vector, and v is a fluid density vector, how many particles passing through that? Just the dot product, right? What was the work done by that linear line segment? Force vector dotted with your tangent vector, right? Same phenomena. Does that make sense? So you have to memorize it. Now you understand it. Maybe you can understand it again on your own, but you better just memorize it and do the rest of the part more efficiently. So do both of them. So I think I wrote down the formula a little bit cleaner. Make sense? This is the formula you have to memorize. P can be very, very tiny size vector, right? And that's how we use the Riemann sum. All right. Here are your challenges. What's different about this problem, you think? Yeah, is the density, fluid density vector is not constant. So is given by this formula. There's no I component, there's no J component, there's only K component. It's always going through upward, right? And we placed our plate, the region down there in XY plane, and this down there is 0, 0. So if you plug in 0, 0 is 2 minus 0 is 2K, right? So around that, density, fluid density vectors are 2 million particles per second is passing through in here for over tiny region. Make sense? Over here is a smaller number is assigned. 1, 1 is almost 0. There's nothing passing through. And here is all changing. Okay? So if I choose the tiny plate down there, tiny plate, does it look like over in here, that looks like delta x and delta y, however it's oriented, turn around. All right, so how many vectors, and what is the number of particles that pass through there? Let's calculate that. Okay. What is, let me turn around the three-dimensional. I think that's easier. Here's a delta x there to that parallel side, delta y there. And what is the obvious normal vector you can choose in there to that plate down there? Z is not a vector. K is a vector. That's right. That's our normal vector, right? And then if it is so small, we assume that fluid density vector is all constant there, right? So we assume that fluid density vector V is all constant. So what is that? It's a phi of x, y, z. That's a fluid density vector, all right? Then we want to calculate number of particles passing through that, right? What was the formula again? Let's remember that one. That was dot product, right? So dot product of, this is a density vector, right? Phi of x, y, z. Multiplied by normal vector k, right? There's no pq in here. If it is just a normal vector, we have to divide the scalar by what? Yeah, the size of a normal vector, right? This will be just the density, correct? This will be just the density. How do you get the number of particles? You multiply the area. What is the area of the plate? Not 1. It's just a tiny one. Delta x times delta y. So if you pick a tiny piece over there and assume fluid density vector is all constant, like this one at that position, then this is the scalar density, how many. So you multiply by the area, you get full number of particles passing through that tiny region, right? So you look at the tiny piece, and what is the next bit? Yeah, all pieces. So what is the Greek notation for that? Sigma and sigma, right? Sigma and sigma. And this one is phi of xy. Let's calculate this one, make it a little bit easier. What is this vector here? 2 minus x squared minus y squared. That's a scalar, right? And k dot k. And what is length of that vector? K, 1, right? That's unit vector upward. And multiply by delta x and delta y. That's a scalar. You can set aside using associativity law. What is k dot k? Also 1. So that scalar is simply 2 minus x squared minus y squared times delta x delta y. That's the number of particles passing through at each arbitrary location. So number of particles is just simply like this for each of them, like that. Now if you just look at this formula and you realize, oh, that's just what? Double integral, right? Double integral over d, that's this region down there, d, right? Of 2 minus x squared minus y squared. This one's dx dy. Just a double integral. So now you know the different meaning of double integral, right? If the vector field is like that, and then you can realize it's a double integral. Number of particles passing through this entire plate. Okay? I have no doubt that all of you can calculate this one. This is 0, 1, 0, 1. Easiest iterated integral, right? That's the number of particles. Put just million in there. Make sense? Any question? Whenever these days, right, the past 3 or 4 days or this week, whenever you see double integral, it's tempting to consider something else, right? What is it? Line integral. What is that? Green's theorem, right? Green's theorem. So number of particles passing through it here is connected to some sort of line integral, right? But what is line integral? Meaning of the line integral? Work done by a force field, right? Down there in xy plane. So around that path, there is some sort of vector field down there leaving in xy plane. Work done by around that, the boundary, work done by that is actually equal to number of particles passing through with a very different looking density force field. This is huge. I mean, this interpretation is really interesting. So let's calculate this one. We want to realize this one is qx minus py, right? That's all you got to do. Right? There are many choices like that. So you can just all do with the qx, but just pretend like this. P and q is completely not related. It's not gradient vector field. So do you see what qx should be to match that 2 minus x squared? 2x minus 1/3 of x cubed, right? Fair enough? And the partial derivative with respect to x is 2 minus x squared, right? How about p? Negative 1/3. No, it's positive 1/3, right? Y cubed. Yeah, the negative is both from there. Make sense? So if p is that and q is that, that's a vector field. You can put it in there. P 1/3 y cubed dx, right? Plus this one and 2x minus 1/3 x cubed dy. Green's theorem says this must be true, right? But what is the meaning of this one? I'm going to use psi, another Greek letter. It's a vector field only in xy plane, such that its x component is this one and y component is the other one. Right? Then is the work done by this vector field. Suppose you live in this two-dimensional world, cannot see what's happening in a higher dimensional world. So everybody got together, try to calculate the work done by this force field down there in xy plane along this path around it. And the guy comes up, and actually, if you enter higher dimension, what it really means is that number of particles passing through the region enclosed by that in a higher dimension. And it happens all the time. In three-dimensional world versus you're passing through four-dimensional space-time. Oh, this is what we're looking at. And if you look at the four-dimensional world, it has completely different interpretation of that you're trapped inside this three-dimensional world with a visual limitation. But if you go higher dimension, oh, that's actually completely different meaning, and they're equal through mathematics. This is very, very deep and difficult to understand. But that's just number of particles we calculated. It has this strange connection down to this vector field down there living in xy plane. All right? Make sense? All right. I have to make this one a little bit more difficult so that we can. So what just changed? Nothing changed except the plate down there was a flat, now is a curved up, right? So D is now this equation, and I wrote it like that to trick you. What is the name of this equation? The surface is coming out of this. What is the name of this? Is it? Not plane, there's a squares in there. Quadric surfaces? Yes, quadric surfaces, right? So there are like 6 of them or something. You got 18% of chance of getting it right. What is it? If it is all square, it's ellipsoid, right? Yeah, there are cones, and how about if I write it like this? Z equals 1/3 of 2 minus x squared minus x squared, right? Can I disregard the constants and focus on x squared and y squared? Name? Elliptic paraboloid again. Right? So here's elliptic paraboloid like this bullet shape, and I just took the little corner of it here. And that's this guy. Alright? So how I'm going to calculate the flux is the following, and pay attention here. We need parameterization of this surface, not region, is a surface, right? Surface is the correct word. Okay? If you have a curve, we parameterize with a t, right? If it is a surface, we parameterize with a 2 variable. And if z is isolated like this, the parameterization is really easy. Let me try this one. His name is Morja. This is Morja parameterization. It's a French guy, right? It's all recorded. You can test it if I pronounce it correctly or not. But this is called special parameterization, M-O-N-G-E, in French mathematician. It's parameterization. So this is how we parameterize. X equals S and Y equals T. X and Y are totally free. Z is dependent, right? So Z equals 1/3 2 minus x squared minus y squared. Just like parameterization of a curve, we use an extra parameter like that. You need one more to parameterize the surface. If Z is isolated like this, you have a nice parameterization. Make sense? So if you have a surface here, we've done this stripping off process in the partial derivative, and I interpreted partial. If I have a point here like that, and if I fix t and only vary s, then it's going to create a curve like that. Okay, so if t is fixed, only s is varying. If I fix s, varying only t, is going to create this curve on it. If you vary freely s and t, you're going to go all over, remain inside the surface. We want this little parallelogram, which is curved parallelogram, right? But we're going to assume it's just a parallelogram. Okay? Tiny perfect parallelogram. We want the side. We want that side. Then we have a P and Q. Then we can formulate the number of particles passing through that guy. So here's my challenge. What is this vector in here in terms of this one? If I call all this one R equals x, y, z, what is this vector in here? It has to do with the derivative, right? Yeah, that's like velocity vector there. Partial derivative with respect to what? If it is t is fixed and s is varying here. Yeah, xs partial and ys and the zs in there, right? That's the vector. But if it is really, really tiny segment, this doesn't make, this is usually like normal size, right? And this is really, really small. And this is harder part. This is a vector, but you have to scale it down to the tiny size. What was the correct scalar? Anybody remember that? That was a delta S. Delta S. It's coming from the definition of a derivative, right? H in the denominator, limit, blah, 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 divided by H. That H is your parameter change, delta X and delta Y and delta S. How about this guy here? Delta T times, yeah, XT, YT, and ZT. Okay? And if I call that one position vector R, this is simply denoted by RS. This is simply denoted by RT. Is that okay? All right, let's go now look at formulate. The number of particles in there is the following. This side vector is delta S times RS, right? That's a vector. This side is delta T times RT. Here is a fluid density vector, phi of xyz. Assume is constant all over here, right? And we don't have like simple k here, right? So let's look at the density first, and let's go to directly to the number of particles. Who remembers the number of particle formula in here? It's coming from orthogonal projection and all that, right? It was actually very simple, wasn't it? It was very simple. What was that? That's right. Here's it. The velocity vector, the density vector, xyz, dotted by, what was the vector again? Cross product, right? And the denominator all cancel out. It becomes really neat. So what was this P here? Delta S, RS, right? Cross delta T, RT. Before it was a P and Q. So that's it. That's the number of particles passing through this tiny region. Okay? These are the scalar, right? So we can factor that out. So it looks like this. Phi of x, y, z. Dotted with what vector? the huge cross product vector, and this delta S and delta S t come out as a scalar product like that. So that's the sizable number. That's tiny number, right? So that's the number of particles passing through that plate there, which is somewhere in arbitrary position, x, y, z. Now we calculate this tiny piece, and what is the next step? The Riemann sum. Riemann sum of this one, dotted with the cross product of these two partial velocity, multiplied by delta S delta t. Then this approaches what kind of notation? Double integral, right? I'm not going to use R. I'm not going to use D. I'm going to use R, right? That's a parameter space. This is for parameter space S and T, not X, Y, or not necessarily that. And then we have to just copy everything down here. This function, fluid density vector dotted with RSRT, ds dt. This is a double integral over the parameter space. If you understand, S varies from, where to where, and here S is exactly X, right? T is exactly Y, so that varies exactly between 0 and 1 here. Okay, so in that case, R and S varies from 0, 1 freely, T varies from 0, 1. That gives you this rectangular region there. Okay, so if you have formulas, we can all plug it in. That's what you're going to do. Now we're going to calculate total number of particles passing through this this surface area, right? Okay, let's do that calculation. S is going from 0 to 1, and T is going from 0 to 1, right? Good. So what is phi of x, y, z? Is that phi is this one? It has only k part, right? And x is s and y is t, so I'm going to plug that one in there. 0 and 0. 2 minus x is s and y is t. Dotted, right? And RSRT. ds dt. And we better calculate RSRT. So what is RSRT? RS here. What is RS? It's over there. So do you see that as a 1? And it's a 0, positive with respect to S. How about this one? Negative 2 over 3, right? X, which is S there. Fair enough? How about T? RT there. 0, 1. 0 there and 1. And if you do that, you have the same thing with a T in it. Fair enough? And calculated that, then now we're dotting it, right? I mean, dotting it, cross product. So what is the cross product of this one? 1, and you do the determinant of the second 2, right? So is that positive 2 over 3s? Is this right? And the second part, you're missing that in determinant of this one, but you have to negate it, so it becomes a positive 2 over t as well. The last one is just simply 1. That's the cross product of these two side parallelogram. Now we're going inside there. 0, 0, 2 minus s squared, t squared. Yeah, it's just so boring answer was just introduced. The ds dt, right? So if you dot it and nothing there, right? And you accept that 2 minus s squared, t squared times 1 and ds dt. Yeah, that's exactly the thing we got with the bottom plate being flat, right? Can somebody look at the picture and explain, and we go? Why is that the same? The number of particles passing through doesn't change. Density changes, right? Density here changes because it's slanted. Density changes, but number of particles passing through doesn't change. Right? Yeah, even if I make this like a bulge like that, you see that? I just blow a bottom there, and then this curtain was created. number of particles exiting out this one is exactly the same. Yes. But it's not same if it is not constant vector like this. If it is sometimes change the direction down there, now it begins to truly change. But if you're going from one direction, changing its density doesn't really change the velocity, number of particles. All right, continue.